Welcome back to the deep dive, where we take the most cutting-edge research, stack up the sources, and deliver the distilled insights directly to you.
Hmm.
Today, we have scored access to something, well, truly fascinating. It's the syllabus and key lecture notes from a high-level post-grad course on large language models fresh out of Stanford.
That's right.
It summarizes the state of the field right up to the end of 2025.
And this isn't just, recap of last year's tech. It's a massive brain dump. It details the foundational architectures, but more importantly, it's charting the emerging battlegrounds of 2026.
Okay, so what are we talking about?
Efficiency, true cross-modality, and the fierce, relentless search for that next architectural leap.
Our mission today is to unpack this evolution for you. The key takeaway right from the start is that LLMs are no longer content just generating text.
Not at all.
They are rapidly consuming the rest of computer science, adapting to images, code, you name it.
But they are notoriously bulky and expensive to run.
Exactly. So we'll cover the fundamental shifts, from how models think about where a token sits in a sentence to how the whole process is being fundamentally rewritten for speed.
And we're going to start at the absolute core, because to understand the current innovations, you really need a quick recap of what powers the intelligence.
Right.
The magic begins even before the main architecture. It's in the tokenization step, dividing the input into those atomic units.
And when you look back at how we used to handle language in AI, you just see why the modern approach was so necessary.
Oh, absolutely.
Older techniques like word-to-vec, they just weren't context-aware. The word bank had the exact same numerical representation whether you were talking about money or a river.
It lacked all sophistication. And that's where sequence models like recurrent neural networks, or RNNs, came in. They processed text one word at a time, building up context.
But they had a major flaw.
A huge one. The limitation was their inability to handle long-range dependency. If a sentence started a paragraph ago, the RNN, well, it essentially forgot the context by the time it got to the end.
That failure point, that short-term memory issue, is precisely what the transformer architecture solved back in 2017.
With self-attention.
Exactly, with self-attention. But for listeners who might have forgotten the mechanism, how exactly does attention let a token reference information from, say, 100 tokens away instantly?
It's actually brilliantly simple in concept. Tokens now attend to one another regardless of their position. It creates a direct mathematical link.
Okay.
The input token generates a query. That query then gets compared against every other key in the sequence. That similarity is quantified using scaled dot products, which are then sort of softened or soft-maxed to create a set of weights.
And those weights do what?
Finally, those weights are applied to the value vectors. It results in a weighted average of all the sequence tokens. The key is that the context is built on similarity.
Not sequential order.
Exactly, not sequential order.
That attention mechanism is the foundation, but the sources point out that even this core idea has been heavily refined since 2017. What's the biggest architectural improvement they highlight in how we track where tokens are?
It's the focus on relative distance, moving away from absolute position.
Right.
Early models gave every token a fixed absolute address, token 1, token 50, token 100. But for language, what really matters is the distance between the tokens.
So if you're asking about a dependency between two related words, that relationship should look the same no matter where it is in the sentence.
Precisely, whether it happens at the start of the sentence, say T1 and T3, or near the end, like T98 and T100.
So you want the relationship to be invariant across the sequence.
Exactly, and that's where rotary position embeddings, or row B, come in.
Row B.
They mathematically rotate the query and keys within that self-attention calculation. This rotation mechanism is specifically designed to emphasize relative positions, making the model far more generalizable when the input sequence gets really long.
Which is crucial for modern LLMs that have to handle these huge contexts.
It is.
Now, speaking of scale, RoPE enables bigger context windows, and the source material spends a lot of time on the economic realities of training these behemoths. What's the current thinking around the famous LLM scaling laws?
The observation still holds true. Better performance, which we measure as lower test loss, it comes from balancing three components: increasing compute, increasing data set size, and increasing the number of parameters.
But there was a catch.
A big one. Researchers have realized that many early models were severely undertrained.
Meaning they weren't fed enough data to justify how big they were?
Precisely. This led to a crucial rule of thumb for training efficiency. You should train on at least 20 times the number of parameters and tokens.
So if you have a 100 billion parameter model, you need to feed it
2 trillion tokens. Efficient training is all about ensuring you feed that monster model enough high-quality data to realize its potential.
And the innovation around efficiency never stops because training these models is still ridiculously expensive. That brings us to one of the biggest economic shifts. Mixture of experts, or MOE.
Right.
It sounds like something only a huge company could manage, but what's the fundamental efficiency gain here?
Think of the LLM as a massive consulting firm. In the old world, for every single question, every single consultant had to read the entire report and weigh in.
That's standard dense computation. You activate every parameter.
Right. With MOE, we have specialized teams, the experts, which are specialized feed-forward networks.
And you have a router.
We do. A router that only sends the input query to, say, the 3 or 4 most relevant experts. So you might train a massive model, say 1.5 trillion total parameters, but per input token, you only activate and pay the computational cost of a much smaller model.
Yeah.
Maybe 200 billion parameters.
Which drastically reduces the total compute required.
It lets you have massive capacity without the massive operating cost.
That's a huge economic lever. But if MOE is a software or architectural fix, the sources also talk about hardware bottlenecks.
Specifically around memory access.
Right. That's where flash attention comes in. Another efficiency breakthrough. Why is memory access such a problem for GPUs?
It all comes down to speed. GPUs have fast, small memory called SRAM, and then slow, large memory called HBM. The self-attention mechanism, just by its nature, requires frequent reads and writes of the key and value matrices.
Constantly moving them between the slow big memory and the fast small memory.
And that memory movement, the I/O, that is the real bottleneck. It's not the actual matrix multiplication.
Okay, so flash attention minimizes those expensive reads and writes to the slow memory. How does it manage that without, losing all the data?
It's a sophisticated hardware leveraging technique that keeps the computation within the fast, small SRAM. What's truly counterintuitive is the core trick.
What's that?
It sometimes achieves speedups by throwing out intermediate results and just recomputing them when needed.
Wait, it recomputes them?
It does, rather than constantly fetching them from the slow HBM memory. It turns out recomputing a small piece is faster than reading the massive state from the slow big memory.
That is brilliant and, yeah, completely counterintuitive. Now, we've talked about making the models bigger and faster, but none of that matters if the model isn't useful or safe. We have to address the alignment stage. After pre-training teaches the model language structure and supervised fine-tuning teaches it helpful behavior, we get to the third, crucial stage. Preference tuning.
Preference tuning is where the model finally learns what not to do, and it's guided by human feedback. This is essential for safety, tone, overall usefulness.
And it relies on reinforcement learning.
It does. We model the LLM as a policy that's predicting the next token or action.
And how do we teach this policy what a good answer looks like?
We need a third model, the reward model, or RM. The RM is trained on human preference data, specifically pairwise comparisons.
Where humans rate 2 generated answers, A is better than B.
Exactly. The RM learns to assign a score that aligns with this human preference.
So we're not just saying this answer is correct, but this answer is preferred.
Exactly. The source material specifically mentions the Bradley-Terry formulation. It's the statistical model used to train this RM on those pairwise rankings. Once the RM is trained, it becomes the metric, assigning a reward to the LLM's output.
And the LLM uses that reward signal to adjust its policy, steering it toward desired behavior.
Be it safety, usefulness, or just a specific conversational style.
Okay, that covers the core foundation, which is, highly refined and context-aware. But the next massive step in the evolution is taking the magic of that transformer architecture and applying it to everything but text.
That brings us squarely to the cross-modal leap. For years, the natural question was, can this attention-based architecture, which was designed for linear text sequences, work for non-text inputs like images?
And the answer was a definitive yes.
A definitive yes with the development of the Vision Transformer, or VIT.
And the adaptation was radical. Traditional image models, CNNs, they were designed with a built-in understanding of local spatial information, what we call inductive bias. The VIT just, it threw that out.
It did. VIT adapted the model by using only the encoder-only part of the transformer. The image is split into fixed-size square patches. Each patch is treated exactly like a word.
It's converted into a vector embedding.
Right, and then positional information is added.
Yeah.
The whole sequence of patch embeddings is fed into the transformer encoder.
So an image is just a really long sentence made of visual tokens.
Conceptually, yes. And what was so remarkable about the VIT success in 2020 was that it worked despite having very low inductive bias compared to the CNNs that came before it.
So it proved that if you just throw enough data at it.
Massive amounts of image-text pairs. The transformer can effectively learn those classification patterns for images anyway. It just brute forces the learning of spatial structure.
And that paved the way for the most exciting user applications, vision language models, or VLMs.
The ability to look at an image and answer questions about it.
The standard, effective approach used in modern architectures like LLVA works by combining these two worlds. You take the image and use a dedicated encoder on it to generate image tokens.
And those were then concatenated with the standard text tokens, like the user's question, and fed into a decoder-only LLM. The model then autoregressively generates the text answer.
Hold on. We need to circle back to speed again, because autoregressive generation, where you predict one token at a time, is fundamentally slow at inference.
Especially for long outputs.
Right. You can't parallelize that step-by-step process. This latency issue led researchers to import a game-changing idea from the image generation world: diffusion models.
The analogy here is perfect for visualization. Think of a sculptor. Diffusion in image generation starts from Gaussian noise, the equivalent of a rough marble block, and learns the process to denoise it into a perfect image.
The sculpture.
The sculpture. It's a series of refinement steps.
But text is discrete. You can't exactly add Gaussian noise to the word cat. So what's the text equivalent of noise that the model learns to clean up?
The source notes that current research points to the mask token as the linguistic equivalent. This creates what we call mask diffusion models, or MDMs.
So instead of starting with noise,
The model starts with a sequence full of mask tokens, a completely blank slate, and learns to unmask and reconstruct the original sentence through a course-defined refinement process.
so it's not predicting the next word, it's predicting all the missing words in a series of fixed steps.
Exactly. It's like generating a rough draft of an entire speech and then refining the whole thing 5 times. Because the decoding only depends on the fixed number of diffusion steps, say 20 steps. Regardless of whether the output is 10 words or 500, it is no longer tied to the length of the output sequence.
And here's where it gets really interesting for people watching performance metrics: the speed up. The source suggests that this fixed step decoding can be up to 10x faster for long outputs. That latency improvement is absolutely crucial for tasks where long code blocks or detailed summaries need to be delivered instantly.
And as impressive as those multimodal breakthroughs are, the war on efficiency just continues within the core training processes, particularly around advanced reasoning. We're asking the models to be not just fast, but reliable.
And reliability often means having the model output a reasoning chain before the final answer, what we know as chain of thought.
Right. This demonstrably improves performance, especially on benchmarks like math and complex multi-step logic problems.
But how has the underlying RL mechanism changed to train for better reasoning?
We're seeing a significant shift in the reinforcement learning field away from the traditional PPO proximal policy optimization and toward generalized reward policy optimization, or GRPO.
GRPO. And what's the key technical difference that makes GRPO more efficient?
Well, PPO requires training a separate, very expensive value model to predict the reward baseline, essentially how good a situation is expected to be. GRPO eliminates that need. Instead, it generates multiple different completions, multiple reasoning chains, and compares their rewards relatively. It only focuses on which completion is better than the others, not how good it is in an absolute sense.
So if the reward is easily verifiable, like, did you solve this math problem correctly, you eliminate the need to train that expensive value model entirely.
You're training a complex prediction model for simple comparison and verification. It simplifies the whole training stack.
It's all about minimizing expense.
And maximizing efficiency. And that pursuit of efficiency reflects the constant iteration happening at the lowest levels of the architecture. The field is still deeply in flux. We're seeing new optimizers, like the muon clip optimizer, challenging the long-standing reign of Adam.
And even normalization techniques are changing.
Right. They are shifting, favoring RMS norm over the traditional layer norm because it uses fewer parameters and is computationally lighter while maintaining performance.
And attention itself.
Even the attention mechanism itself is evolving beyond the simple multi-head design, with techniques like grouped query attention, GQA, becoming common to save time on computation.
But here's a serious structural crisis that all these new, faster models are facing: the data quality crisis. The sources indicate that the internet, The model's training ground is rapidly becoming saturated with LLM-generated text, synthetic text. Some estimates suggest it might be up to 80% in specific search result categories.
And the consequence of training next-generation models on this synthetic, less diverse text is, well, it's catastrophic. It leads to model collapse.
Explain model collapse for us. Does the model just break down?
Not instantly, no. But the learning quality degrades dramatically. Imagine training a student only by having them read poorly summarized versions of classic texts that other equally rushed students wrote.
They lose the nuance.
They lose the nuance, the originality, and the depth of the original material. When a model trains on its own, less diverse reflection, it enters a feedback loop, resulting in a loss of meaningful learning.
That's a massive problem that risks crippling future generations of AI. So what are the solutions being explored right now?
They involve intensive data curation, ensuring new data sets are heavily screened for synthetic content. But the most interesting fix is inserting mid-training stages based on smaller but extremely high-quality corpora
Essentially forcing the model to reground itself in human reality.
before it ventures back into the noisy synthetic data.
This all leads directly into the biggest current economic challenge: cost. Making LLM predictions cost-effective is the mission of what the sources call the second Pareto frontier.
Right, favoring small language models, or SLMs, that can perform high-tier tasks cheaply.
The current GPU architecture is the elephant in the room here. We talked about flash attention as a software fix, but the field is now focused on radical hardware redesign because of that same key-value memory movement issue.
Yes, GPUs excel at matrix multiplication, but the memory I/O remains the bottleneck for attention.
So we need hardware built specifically for the attention mechanism, not just for generalized matrices. What does that future hardware look like?
This is where we get into some mind-bending physics. We're seeing proof-of-concept architectures that are embedding computations directly into the physical hardware itself using analog signals.
So not digital ones and zeros.
No, they rely on physical properties, like using current flow and resistance governed by laws like Kirchhoff's to represent and perform computations.
So the computation becomes a physical side effect of the signal passing through the circuitry rather than a calculation performed by a switch.
Precisely. You avoid the energy cost and latency of digital switching and explicit memory reads. Simulations show this yields significant, almost instantaneous improvements in both latency and energy saving.
Which could potentially make future SLMs cheap and fast enough to run on every device.
That's the goal.
That paints a powerful picture of intense parallel development, doesn't it? The core strength of the transformer architecture is proving its versatility across every modality, from text to images, while the entire industry is simultaneously trying to shrink the cost and speed up inference.
Using everything from software tricks like diffusion models to total hardware redesigns based on analog physics.
Absolutely. The main takeaway for you is that the utility of LLMs is no longer confined to just chat interfaces. We see the push for user-facing agentic workflows, coding assistants that write and test their own code.
And general assistants that can manage complex multi-step tasks. This is how these complex capabilities get truly democratized.
But the sources remind us that the hard human challenges remain. Even with all these advanced training techniques, stabilizing those multi-step agents is still really difficult.
And embedding human values like true empathy and nuanced judgment into something like an AI customer service agent remains a very high bar to clear.
And that ties perfectly back to the foundation we discussed today for the final thought we want to leave you with. We learned that LLMs are fundamentally trained to predict the most probable next token using probabilistic models, not to map statements to external verifiable facts.
Right.
Given that core design, should we stop referring to hallucination as a flaw or a bug that needs to be fixed, and instead consider it an inevitable, even core design choice of this current generation of autoregressive models?
Something to mull over as you watch this space explode with new innovations.